Hello everyone, hope you all are doing well and enjoying the new chapter Statistical Thermodynamics. Now time for the lecture number 2 where we're going to discuss entropy and thermodynamic probability. But before that, I would like to start from the last slide of the first lecture where a problem was given. The problem was take a system having 4 coins, rupee 1, rupees 2, rupees 5 and rupees 10 where 3 coins are tossed together at a time. So we have to find out the probabilities such as the number of macrostates and microstates. Okay, so you have 4 coins, out of them you have to take 3 at a time. So it's simple combination 4C3. So the result of 4C3 is factorial 4 divided by factorial 3 divided by factorial 4 minus 3. So the result is 4. How these 4 are constituted? You take in a frame 3 coins, 1, 2 and 3, 10 is out. Okay, then 2, 5 and 10, 1 is out. Then 1, 2 and 10, 5 is out. And finally 1, 5 and 10, 2 is out. So keeping any one of them out of the system, the rest of the 3 constituting the macrostate. So for 4 coins, 4 times you can take them out of the system, so 4 number of macrostates can be constituted. Now let us consider the macrostate number 1 where, as for example, we have taken rupee 1, rupees 2 and rupees 5. So toss them. So first probability is head of all the 3 coins. Second probability, tail of all the 3 coins. Third probability, head of the first 2, tail of the third one. Then fourth one is head of the first one, tail of the rest of the 2. Okay. Fifth one, this way you can combine them and you will get finally 8 numbers of combinations. Head, 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 tail, tail, then tail, head, 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 tail, head, tail, head, tail, 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 tail. This way 8 numbers of combinations. So each macrostate would correspond to 8 microstate. Okay, so number of macrostates is 4 and each macrostate would have 8 microstates. So all are equally probable. Now in this regard I would like to say one more thing. Just take this into consideration very minutely, so that how we would combine 2 systems. When you would combine 2 systems, then how would you would calculate the probabilities? Probability is a multiplicative property. Suppose take the example of 2 dice. The probability of a single die was 1 by 6. But when you throw 2 dice together, then the probability becomes 1 by 6 into 1 by 6. That is 1 by 36. Isn't it? So this way you can understand the fact that probability is a multiplicative property. But take into consideration entropy. Entropy is such a thermodynamic probability which is additive in nature, isn't it? So next our topic of discussion is probability and entropy. As I have said that probability is the degree of disorderness, and since thermodynamic probability is also similar to that kind degree of disorderness, so they should have some connection in between them. So let us take into consideration that W is the function of entropy. Okay, since entropy is the measure of disorderness and a disordered state is more probable than complete orderness, entropy or S can be considered as a function of thermodynamic probability W. Therefore S equals to function of W. This is equation number 1. Now take 2 separate systems and apply equation number 1 to both of them. Suppose these 2 systems, separate systems having entropies S1 and S2 respectively, and their corresponding thermodynamic probabilities are W1 and W2 respectively. So if you apply equation number 1 to both of them, so for system number 1, their equation should be S1 equals to a function of W1, and for system number 2 the equation should be S2 equals to function of W2. So thus we get equation number 2 and 3. Okay. Now these 2 systems are combined together to have their combined entropy. That means now you combine these systems, 2 systems, and you get a single system. So what should be the entropy of the new combined system? If you take that the entropy of the new combined system is S, and the same for for the combined system the thermodynamic probability is W, then we can write, as I have said, that entropy is an additive property while probability is multiplicative property. So this way you can get equation 4 and 5. You are adding two entropies to get the combined entropy, while you are multiplying two probabilities to get the combined probability. So S should be S1. If S is S1 plus S2, then W must be W1 into W2. Okay, thus you get equation 4 and 5. Now you put these values, okay, in equation 1 and 2. What was the value in equation 1? Equation 1, 1, 2 and 3. Equation 1 was S equals to function of W. Equation 2 was S1 equal to function of W1, and equation 3 was S2 equals to function of W2. In this equation 1, just put these values. Okay, instead of S you are writing FW. Instead of S1 you are writing FW1, and instead of S2 you are writing FW2. So from equation 1 and 2 you are getting some values of S, S1 and S2, and putting these values in the form of W, W1 and W2, and thus you get equation number 6. Okay, so putting the values of 1, 2 and 3 in equation number 4, we are getting equation number 6. Now let us proceed further. Instead of W you can also write W1 into W2. So we are writing here to get equation number 7, putting W equal to W1 into W from equation number 5. To satisfy this, now you get this point that some function of two parameters which are multiplied with each other, while the result is addition of function of two parameters separately. That means function of W1 W2 is function of W1 plus function of W2. This type of property is possible only when it's a logarithmic property. As for example, log xy is equal to what? It is log x plus log y. So only for logarithmic relationship this is possible. Now you cannot directly say that S equals to ln W. Okay, you have to add with this. You have to just, like some spice, adding some spice, you have to add some constants with that, okay, to make it more tasty or to make it more logical. So you have to consider two constants k and c. This way, to satisfy this condition, it is obvious that the function must be logarithmic, and hence it is possible to write S equals to k ln W plus c. That is, we could have written S equals to ln W, but we have to take into consideration some constants such as k and c, and this k was found to be later it was found to be equal to the Boltzmann constant, that is the molecular gas constant. R is the universal gas constant, molar gas constant, but k is the molecular gas constant. When you divide R by N0 Avogadro number, then you will get k. This is known as the Boltzmann constant. Later it was found to be Boltzmann constant. So this k is Boltzmann constant, but we do not know the value of c, so we have to find out the value of c from equation 8. Okay, so as I have said, this is mentioned, this is written here, k is the Boltzmann constant. Now let us find the value of c. Now equation 8 can be applied to both the systems individually and by adding them the equation for the combined system as well. So for system number 1, if you apply equation number 8, then first system should be S1 equals to k ln W1 plus c, and for the second system it should be S2 equals to k ln W2 plus c. Now combine them, just simply add them. So in the left hand side you will get S1 plus S2, and in the right hand side you will get k ln W1 plus ln W2 plus twice c. This is equation number 11. But ln W1 plus ln W2 is what? Ln W1 plus W2, W1 into W2, and W1 into W2 is W, we know. So let us see. Yes, here they are written here that S equals to k ln W1 into W2 plus twice c from equation 11, or S equals to k ln W plus twice c. So instead of W1 into W2, we are writing here the probability of the combined system W. So thus we get equation number 12. Now equation number 8 was what? Equation number 8 was, yeah, some technical problem anyway. So what was equation number 8? Now S K ln W plus C. S K ln W plus twice C. So the left hand side, both of them are S, and in the right hand side, in equation number 8 it was K ln W plus C, and in equation number 12 it is K ln W plus twice C. That means C equals to twice C, or twice equals to C. That means twice C minus C equals to 0. So what is twice C minus C? Twice C minus C is in turn C. That means C equals to 0. So in both equation number 8 and 12, if you put C equals to 0, then you will get equation number 13. And this is the desired relationship of entropy and thermodynamic probability. So this is very important relationship, and you have to derive them properly. So the relationship is S equals to K ln W. Now you have to plot this graphically. You have to present this graphically. What should be the graphical presentation? It would give a logarithmic curve. If you plot W in the x-axis and S in the y-axis, then it will give a logarithmic curve. But there will be no negative y-axis, because the minimum value of W is 1. Okay, for any system, the minimum number of macrostate as well as the minimum number of microstate is always 1. So for 1 it is 0. So at W equals to 1, S equals to 0. So let us see how about the graphical presentation. So this is about the graphical presentation, where at this point the minimum W is having its minimum value 1, and the corresponding value of entropy is 0. And here it's a logarithmic curve, and here at this point S reaches, that means entropy reaches the maximum value where there is no change in entropy. That means delta S equals to 0 at maxima. So this is the graphical presentation. Okay, so at equilibrium, and definitely this is the equilibrium point. At equilibrium, W equals to maximum, or ln W equals to maximum. If ln W is maximum, then S is also maximum. Therefore ds or delta S equals to 0. So that's all for this topic, entropy and thermodynamic probability. Thank you. Have a nice day.